Hi, this is Emily, and today I'm going to be showing you how to do question number 15. So this is the diagram from the book, and the first thing I'm going to be doing is drawing in all the forces acting on each particle. So each particle has a weight, and there's also tension on each particle, which is pulling the particle towards the connection point. Because of geometry, we also know that the vertical and the tension form an angle of 5 degrees. And with this angle, we can now solve for the components of tension. So we know that the y component of tension on each side is tension cosine 5 degrees. And the x component of tension on each side is tension sine 5 degrees. There's also an electrical force that's repelling the objects. And we know that the force is repelling the objects because the objects have the same charge. And as you can see, this diagram is extremely symmetrical, meaning that the forces acting upon each object are the same. So we're just going to consider the right side right now. We need to set a positive y direction and a positive x direction. And right now, let's add up all the forces acting in the y component. So the sum of the y forces is equal to t cosine 5 degrees minus the weight. And we know that the total amount of force equals 0 because the object is in equilibrium, which means it's experiencing 0 acceleration. And so if we plug in the known values of mass, which is 0.002 kilograms, and gravity, which is 9.8 meters per second squared, we can solve for tension. And we get the tension is approximately 0.0196749 newtons. Now let's add up all the forces in the x component. So we have the electrical force minus tension sine 5 degrees is equal to 0 because, again, it's in equilibrium. And if we plug in the value we got for tension before, we get that the electrical force is approximately 0.001715 newtons. And as we know from before, the electrical force is equal to K, which is a constant, times Q1, Q2, all over the radius squared. So we know that right now we need to find the radius if we want to set these two electrical forces equal to each other. So the radius is just this small section right here. Oh, wait, sorry. The radius is this entire section over here. And to make that easier, we're going to find this small section right here. So in order to make this easier to see, I'm going to draw just the right side of the diagram. We know that this is 0.3 meters, and this is 5 degrees, and half the radius is this. And we're just going to call this x right now, which is equal to 1/2 the entire radius. So in order to solve for x, we can say that sine 5 degrees is equal to x over 0.3 meters. And when we solve for x, we're going to get that x is approximately 0.02615 meters. And that means that r is approximately 0.05229 meters because r is 2x. So we can write the equation for the electrical force now. And we can plug in K. And remember that these Q's are going to be the same because the particles have the same charge. So we can just say Q squared over R squared. And remember that R is 0.05229 meters. And remember the FE we got from here? Well, we can set this FE equal to that FE. So is equal to 0.1715 newtons. And because K is a constant, we can now solve for Q. And when we solve for Q, we're going to get Q is approximately 7.218217 times 10 to the negative 9 coulombs, which is equal to 7.218217 nanocoulombs. So each particle has a charge of this many coulombs. Yay!